Hello, everyone. Welcome to the Knowmads Podcast. I'm your co host, Prachi.
And I'm your co-host Bhavay.
Chaos is one of those words that has escaped physics and entered everyday language. We use it to describe messy rooms, traffic, even our inboxes. But in physics, chaos has a very precise meaning. Or does it? Well, classically, chaotic systems are those that, even though they are completely deterministic, they are extremely sensitive to their initial conditions. Even the tiniest change in the initial conditions can lead to wildly different outcomes. But when we move to the quantum world, things become a little strange. When there are no deterministic trajectories in the quantum world, how do we even make sense of chaos? Our guest today is Dr. Marine de Clerck, a mathematical physicist at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. Her work lives right at the intersection of chaos, gravity, and how mathematical structure is built upon quantum chaos. So if you've ever heard of the butterfly effect and wondered what chaos really means, you're in for a treat. So let's go.
Marine, welcome to the Knowmads Podcast.
Thank you.
But let's start by telling the audience why we're here. So I'm attending summer school. It's the advanced school in integrability, quantum chaos and complexity at University of Warsaw. And you're one of the lecturers. And you lectured on arithmetic chaos. So let's start by unpacking what arithmetic chaos is. Or, let's start with what chaos is. So chaos is, the word chaos is used very colloquially in the English language. A lot of people say the word chaos. And in physics and mathematics, chaos is, especially, if not well-defined, but much more defined than it is, in its general language. So why don't you start telling us about what chaos is and how do you think about chaos?
So, classical chaos is, I guess, the thing that people have in mind, or at least the first example that physicists use to explain what chaos is the weather, where you know that the weather is very hard to predict for long times, and that's because the equations that govern these dynamics are nonlinear and are chaotic. And so that's one of the very important aspects of chaos, and it's the fact that whenever you slightly perturb the system, this perturbation can grow exponentially, and that directly means that if you have a small error in the measurement of the system at some instant of time, this error will propagate exponentially and will or might lead to wrong predictions if you wait long enough. So that's a basic fact of why weather is hard to predict, and that's a generic feature of chaotic systems, that they have a very strong sensitivity to having slight errors in the initial conditions, and this error will propagate exponentially with some specific coefficient, that exponent that is specific to the dynamical system you're looking at.
Okay.
So that's one of the definitions, I guess, the sensitivity to initial conditions, and this exponent that people associate to a specific to a given system. This exponent is called the Lyapunov exponent. But that's I guess that's one of the definitions, and that's the definition that I'm most used to. But it's a difficult problem. It's basically trying to, the whole area of dynamical system is a difficult one, and it's very hard to come with definitions that will be appropriate for every single system that might display chaos. So that's one definition that I know of, and that I'm encountering in my daily life.
Okay.
So that would be the go-to answer, I think, when people ask what is classical chaos.
Right. So you mentioned classical chaos, but there's also like a quantum aspect of chaos, or there should be, some quantum aspect of chaos. Let's call it that. So tell us why we cannot define quantum chaos the way we can define classical chaos that you just did.
Okay. So I guess the first answer to that would be that of course, the equations and the formalism of quantum physics is totally different to the framework of classical physics. One of the key concepts that you need in classical physics to describe what chaos is the fact that you start with some initial condition and you follow the evolution of this initial condition as dictated by the dynamics of your model. And this evolution in time draws a trajectory, and the very concept of trajectories in phase space is not something that is that you can define in the quantum framework. So already at the level of just the definition, you can see that the usual way will not work in quantum physics, because there's just no concept of specific trajectories in quantum physics, and that comes down to the fact that you have the Heisenberg uncertainty principle, and you cannot define both a momentum and a position at the same time to arbitrary precision in quantum physics. And that's why you need to pinpoint one point in phase space in classical physics to slightly perturb and evolve the two points and see that they would diverge exponentially. So that's the main issue of directly translating this specific definition of classical chaos to the quantum realm. And so, physicists have tried for many decades now to try and understand what definitions would actually be good ones. Because, of course, if you have some classical evolution, you know that this should be some effective description of some quantum dynamics that is in the limit of small h bar or something will lead to this specific classical dynamics. So there should be some concept of quantum chaos that leads to this classical chaos, and the whole area of quantum chaos is trying to understand what type of things you should define in the quantum theory to be able to describe what you find in this classical theory.
Right. So again, what are some of the ideas that are floating around to tackle this problem? And as you said that, any in order to have any characteristic of quantum chaos, its classical counterpart should also be chaotic, or is that how you also think about it in terms of this BGS conjecture?
Yeah. So I think it definitely okay. So while it is true that if a system is classically chaotic, there is this BGS conjecture that conjectures a certain behavior for specific probes in the quantum theory. So what are these? So I guess I'm familiar with mainly two type of things you could try compute in quantum systems to try and determine whether it has a classical or a chaotic limit in the classical limit. Namely, one of them is related to this conjecture that tells you to forget for a minute about the Lyapunov exponent and so on. Just focus on the quantum system you have, on the Hamiltonian, and on its eigenvalues. So the quantum system will have some discrete quantized spectrum of energy eigenvalues, and the claim is that systems that have chaotic or integrable classical limits will display a different type of statistics for these eigenvalues. So there's just certain statistics that you have to look at. So to be specific, you should look at differences between neighboring eigenvalues and the statistics thereof. So make a histogram of, so you're given a Hamiltonian, you try and compute its eigenvalues, you order them, and then you look at the spacings of neighboring eigenvalues, and you make a histogram of them. So there's, of course, some process you have to do that. It's called unfolding, but let's not complicate things. In spirit, it's just having to do with how eigenvalues are spaced. And the claim is that for quantum models that have a classically chaotic dynamics, this curve will look like the so-called Wigner surmise, whereas for integrable models, the claim is that the eigenvalues will be pretty much uncorrelated because of all the conserved charges that you may have in your system. That makes it integrable. And because these eigenvalues are uncorrelated, the spacings will be basically follow Poisson distribution.
Okay. So that's the only characteristic? Well, that's part of this conjecture.
That's part of this conjecture, yes.
Right. And is there any other characteristics that these systems have?
Okay, so this was specifically about the very late time dynamics, namely the spacing of neighboring eigenvalues. And of course, as I was talking about in these lectures, there's also some other probes you can have a look at that always have to do with basically correlation functions of the density of states. And specifically, you have, for example, this 2-point function, the Fourier transform thereof, which is called the spectral form factor. This also has a very specific feature at early time. It has this linear ramp. And this is also related to random matrix theory as well. So models, chaotic models, if you look at their statistics, if the model is chaotic, you will expect it to, of course, it's been understood that you should expect it to show some similar features to what random matrix theory would tell you, that randomly drawn matrices from this ensemble would look like, so that effectively very complicated Hamiltonians mimic very well these random matrices and their spectral properties.
Okay.
So that's all about chaotic models. And then for the integrable models, well, I guess if you're looking at eigenvalue spacings that are uncorrelated because of a tower of conserved charges that you may have, then you will see it give a Poisson distribution as opposed to the Spegner-Nielsen distribution. And that will hint to the fact that there's actually some conserved charges that you did not take into account in when looking at the spectrum. And so, for example, say you have a model which is not quite integrable, because sometimes you just don't know, right? Sometimes you're giving a Hamiltonian, you want to study some Hamiltonian, you don't know whether it's chaotic or integrable. So one of the things you might do is just have a look, try to diagonalize it, which may or may not be done, but if you can do it, if it's, say, a finite dimensional model, you can put it on a computer and you diagonalize it.
Okay.
Then the first thing you might try to do, if you're interested in its chaotic properties, is to look at the spectrum, and you might find Poissonian, even if it's not integrable. It could just be that there's some conserved charge that's there that has nothing to do with some tower of conserved charge. It's just conserved charge that your system happens to have. And in that case, what you have to do is try to find the different sectors in your spectrum. So all the eigenvalues, given that you will have one conserved charge that commutes with the Hamiltonian, you can consider a joint eigenbasis of these two. And then you just have to look at specific sectors that all have the same eigenvalue of this one conserved charge, additional conserved charge that you have, and then you have to do the spectral statistics for this on its own, because all the different sectors, the idea is that they're uncorrelated. So whenever you take them all together, it'll basically alter the statistics, and it'll make it look like it's Poissonian and that they're all uncorrelated, but in fact you just superposed multiple correlated sets of eigenvalues.
I see.
And so in that sense, it's not because you have Poissonian that you'll be integrable, but if it's Poissonian, it means there's most probably some conserved charges that you need to take care of.
Right.
Then the question is, once you've taken care of those that you can find, can you find more, or will it be Wigner-Dyson? Will it have this specific level repulsion that is associated to these chaotic models or not?
Right. So spectrum of eigenvalues and this spectral form factor that you also mentioned. So apart from these, what are some other probes that you can use to understand chaos in a system? So what are some of the other quantities that people study that can at least differentiate between an integrable and a non-integrable system? Also tell us what's the difference between an integrable and a non-integrable system.
Okay, so, one of the probes, the level spacing statistics should be viewed as a late time dynamics probe, because it probes very nearby energy levels. So by the usual Fourier transform between the two, late times means small energy gaps. And so next to these late time dynamics, you can also try to find some early time probe, and that would be closer to the classical story that we talked about before. Namely, there is something like a quantum Lyapunov exponent that you could try to define.
This is for early time, right?
This is for early
time,
times,
yeah,
because it'll track the exponential divergence. Well, in the semi-classical limit of your model, where some trajectories might start making sense, it will track the exponential divergence of neighboring trajectories. But in the quantum version, there is a way to try and make sense of this specific time dependence in terms of some specific correlation function you have to compute, which is not time ordered. So it usually goes by the name of out of time ordered correlator.
Right.
And one of the proposals was to have this early time probe compute a 4-point function of some local operators where you time evolve some of them in a non-ordered way. And the claim would be that whenever you have a chaotic model, you have some positive Lyapunov exponents. But this claim, so this would be really to try to mimic this classical story. I will give you information about the early time behavior of how your model responds to some early perturbation. So there's some sense in which you can understand this 4-point function as applying some initial perturbation and trying to track it down with the other operators that you insert. But it's been understood now that this probe is not always a very good probe. Namely, it's a very good probe whenever you're in the semi-classical limit,
right?
Or whenever you have a large number of local degrees of freedom. But for example, in just a spin-1/2 spin chain, which is a very well-known model that condensed matter people like to look at, you just don't have this exponential growth because the local Hilbert space is just too small. So while it has a lot of nice features whenever you're in some large n limit of some model,
which is a semi-classical limit.
Yes, yeah. which then turns the model into some semi-classical model. Then it usually works well, and especially in the context of black holes, which is also where I'm coming from. It has led to nice results and to nice understanding as well of this particular probe, because then people started to think more about it and so on. But it's not always useful if you're just given a quantum model that does not have some classical counterpart, for example. Right. It's not always clear that you will be able to distinguish in a concrete way the classical and the chaotic and the integrable models. So
there's like the late time behavior actually gives you a more concrete answer. Is that the correct way to understand?
The spectral statistics gives you a different type of information. It's just something about the late time physics. I guess we heard in the lecture today that it was also not always telling you the truth about what you want to know. But it's I think one of the most interesting questions nowadays as well is to try and understand quantum chaos is a difficult topic. There are these different types of probes. We only touched on two of them, and those are also, I think, the most well known, at least in my community. But there isn't always an understanding about how these various probes connect to each other, how one would imply the other, and so on. So the topic of quantum chaos is very rich, has a lot of proposals of how to distinguish chaotic from classical systems, but it's not always clear how the different probes connect to one another, and that should be one of the aims of the community, and it is.
I see. So that's great. That's nice. That's a nice elaborate answer. The other thing that we study and I want you to elaborate on is the concept of operator growth, and how this whole chaos story sort of ties into complexity, what complexity is, and how do you think about these things?
Yeah, so I think, trying to understand chaos versus integrable, it's of course, I think one of the motivation is mainly to try and have some more understanding of the dynamical models that we look at. And one of the reasons you might care about this is because usually what people want to do is to try to be able to simulate systems, right? To try and understand how they work and how to efficiently simulate things. And that's pretty much related to complexity, because complexity is about, say you have some Hamiltonian evolution of your system. One of the probes, for example, that I'm familiar with and that I've worked with is the concept of Nielsen complexity, where you look at, for example, the evolution operator, so exponential ITH, and you view this as some matrix in the group of unitaries. And of course, at t equals 0, you start at the identity. And then as t evolves, you draw sort of a path into this manifold of unitaries. And then the question that you answer in using Nielsen complexity is what is the distance on this group of unitaries between the identity where you started and the evolution operator exponential minus ITH at some time t.
Right.
And of course, you can always follow the path that you just drew and compute the distance thereof, but it might not be the closest geodesic path between the identity and this operator. So that means if it's not the closest, the smallest distance path, that means that there's a more efficient way to go from the identity to that operator. And that's what basically complexity is about, to try and understand how can I efficiently generate this evolution. And it all comes from, so what I'm talking about is now maybe a bit abstract, but it really comes from the circuit complexity type of view, like where people have circuits in mind, and to get from one state to another, what would be the smallest amount of building blocks I have to assemble to be able to reach from one state to another. And so if you start with a given set of building blocks to work with, usually there's the shortest path that you can construct, and that would be a measure for how complex the end state is compared to the starting state. And in the case of chaotic versus integrable, I guess the question, formulated, for example, in terms of this Nielsen complexity, the question would be, does the Hamiltonian evolution of a chaotic model and the Hamiltonian evolution of some integrable model, do the complexity of these evolution, are they the same? Are they not the same? The expectation is that they're not the same, because the integrable evolution is in some sense, the intuition is that it should be simple, because it's supposed to be very regular, whereas for chaotic models you expect it to be very complex. And so the complexity is some type of measure that is expected to saturate at some point. And so one expectation you might have is that integrable models will saturate at a lower value, so that at some point it just keeps on being, of lower complexity than the chaotic models. And so this is something you can make concrete in some models, but it's usually a hard quantity to compute. And that's why people have also looked at this K complexity, like the Krylov complexity, which is another measure of complexity, which you expect the same type of features, distinguishing chaotic and integrable from, for example, the size of the plateau, like the height of the plateau, the saturation behavior. But it's arguably easier to compute in cases. And I mean, I say arguably, but I think it is easier to compute. But it's a different probe, and I guess, as usual in all these areas of quantum chaos, it's also not always clear how to connect these different types of complexities. Usually, there may be some mentions about the fact that one notion of complexity will be polynomially related to another notion of complexity.
Interesting.
But these type of proofs are not always so easy. Like, for example, Nielsen complexity has this type of relations to circlet complexity. So this is something that Nielsen to some degree proved in their papers, Nielsen and collaborators. But I haven't worked on Krylov complexity, so I don't know the status of precisely the status of what has rigorously been proven about how they relate. But usually people expect that different notions of complexity will be related polynomially with one another, so that whenever you have some exponential growth, for example, you can definitely say this is a different type of behavior than just some polynomial growth.
I see. So Nielsen complexity has, like, you started off by saying that it has this nice geometric sort of intuition in this manifold of unitaries and so on. Is there a similar intuition for Krylov complexity?
No, not that I know of. But again, I haven't worked on it.
Okay, that's fair.
But yeah, I guess it was mainly what Julian Sorner has been lecturing about. So yeah. I
see. So a slight technical question on Nielsen complexity. So what how do we define like a metric on this space?
Yeah, no, it's a good question, because the choice of metric actually will, I mean, it is the most important question really in this story, and it is also related to one of the critics against this approach, because there's, so just on the manifold of unitaries, there's a canonical metric that you can write on it, and it's so-called a bi-invariant metric by its invariance properties, by multiplying by some unitaries or something. But that's actually not the metric. So it's a canonical metric, but it's not quite the metric you want to use in this story, because you want, in the back of your mind, you have this circuit complexity intuition, where if you notice the words I was using there, I was saying that you have these small building blocks with which you will create more and more complex gates. You will assemble them so that you can reach a state from a given state. You'll be able to reach another state, say. So you have these building blocks you start with, and those are usually viewed as local operators. So in circuits, in the realm of quantum gates, you usually have a set of simple operators you can actually construct in a lab and easily manipulate.
Right.
And then you have to assemble these to make more complicated operations.
I see.
And of course, if you have to assemble them, that means that the cost will increase. So the easy ones have low cost, and you have to assemble them to create more complicated operators, and then these will have a higher cost, a higher complexity, and because given any state you can reach another state, you can always reach another state by some operator, right? So then if you don't say that you'll only consider building blocks that are easy, everything will just have complexity 1, right? So that's why it's important to have a notion of some easy operations that you can do that will have some low cost. And then the question is how to construct more complex operators by assembling them in the most efficient way. And in Nielsen complexity, you have something similar. So instead of having just any direction being having the same cost, you will say that some operators will be called easy. It will define easy directions, and other operators will be hard, define hard directions. And so you will write down a metric that differentiates between these two directions. And so then this type of metric is called right invariant, and it basically means that it differentiates some directions from others by giving them a harder, like a higher cost. The geodesics will tend to try to want to go in the easy directions. And that's the way in which you'll be able to force the geodesics to be constructed, roughly speaking, in terms of these easy operators. Of course, it's some continuous thing, so it's not as discrete as the gate stuff, but it's one way to try to mimic this story, and that's also in this setting that Nielsen was able to say some rigorous things about how these two types of complexities relate to one another.
Very interesting. So moving on, how does so while unpacking arithmetic chaos, so where does arithmetic fit into this whole picture? What's that word all about?
Yeah, so well, I guess it really comes from the setting, so the specific dynamical model that we are looking at, and that will display this arithmetic quantum chaos. Namely, arithmetic chaos or quantum chaos appears in the setting of billiards defined on some hyperbolic domain. So simple single particle billiard motion, say in the classical sense, on a hyperbolic domain. So not on Euclidean space, but on 2D hyperbolic space.
Okay.
And the arithmetic part comes from the specific boundary conditions that we will apply. So specifically where you locate the walls of this billiard on the hyperbolic domain. So on the hyperbolic 2 plane. And well, of course, it's a bit technical then, but the specific domains that will display this arithmetic chaos are related to what is called the fundamental domain of some subgroup of SL2Z, which is the group of modular transformations. And so it's really the Z part which is important, and the Z means the integers in the reals. And the fact that you have this discrete thing, the integers in the reals, is what will lead to a plethora of special features that will ultimately lead to arithmetic chaos. And specifically what distinguishes arithmetic quantum chaos from other systems is that its classical limit is chaotic. But if you look at spectral statistics, for example, you will see that it looks as if it's integrable, so the shape will be Poissonian when you look at nearest neighbor statistics. But so it looks like it's integrable, but it's not. So it's just one of these cases where the probe that you're looking at doesn't actually tell you what the classical limit, what type of properties the classical limit has, because classical billiards on 2D hyperbolic space are go-to example, like textbook examples of systems that have ergodic motion and are chaotic. So yeah, classically it's well understood that it's chaotic and ergodic and so on. But then if you look at these specific boundary conditions that have to do with SL2Z, somehow you find that the spectral statistics give you Poisson statistics.
I see. So I think it's a good point to zoom out of this and maybe talk a little bit about why understanding. Why before we get to what you specifically work on. But I think it's more important to get this bird's eye view on why understanding aspects of chaos is important. And if you have any examples that understanding chaos that this will become relevant to solve some particular problems in physics, according to you, what those problems are, and why should we care about understanding both quantum and classical? Well, classical is slightly better understood. Why do we want to understand quantum chaos?
Wow. Okay. I think as a physicist, the first physicists were people who tried to understand the behavior of dynamical models, right? That's like whatever Newton, whatever he cared about was to understand motion, right? So chaos, classical chaos at first is just a branch of the study of dynamical systems.
Right.
So it's a very fundamental thing to try and understand how different models fit into different types of classes. Whatever you see at school, usually you see these systems that you can solve exactly, and that just doesn't turn out to be the most generic thing. Generically, you will not have systems you can solve. You will not encounter in nature integral models that you can just read the solution for, but you will find chaos, you will find complex motion, and it is definitely important to try and work out some tools to know how to characterize them, how to describe them, how to understand how to actually predict and know what the limits are of what you can predict. For example, I mean, chaotic models are deterministic. So if you're strong enough to know to arbitrary precision what your initial condition is, you will be able for a long time to track what the evolution is.
Right.
So it's definitely important, especially if day-to-day life in the weather, is super important to be able to say how long am I supposed to trust whatever result I'm predicting.
Right.
So, okay, that's just basic reasoning of why classical things are important, dynamical systems, why it's important to understand them well. And then quantum mechanically, of course, we know fundamentally that the classical theory is just an effective description of what is really quantum. So it's a very natural question to understand how these classical features arise, and for this we need to understand at the quantum level what's happening.
Mm-hmm.
And it just turns out that the type of tools you need are different, and then it's that in its own is already interesting.
Right.
But then, of course, you have to come up with ways to connect. Well, first to connect these two pictures, and then, of course, this. Whenever you delve into it, you see that this just brings that this opens up a whole new world of new questions, and then you find new quantum phenomena that you didn't even imagine because you didn't see them in the classical world. And then, of course, if you're curious, then opens up a lot of questions that you have to answer. So, I guess for specific open problems, I think within quantum chaos, I think it won't be about, at least not for me, maybe for a specific condensed matter person, it will be a specific system that they really want to solve. But for me, the things I'm getting in contact with is really to try to understand the connections between the various fields or the various probes that you have.
Right.
Because as long as you only have very sort of sporadic things, you can't claim that you understood what is happening. You can have observations and try to build a framework to describe these observations.
Mm-hmm.
But at that point, you haven't understood what is quantum chaos. And at this point, nobody knows what a good definition is of quantum chaos, even at classical level. It's not always clear. So,
Yeah. So the one way I sort of also convince myself is that, it's such a ubiquitous feature that basically everyone just experiences it every day, but we're just not, we don't care about it. So anyways, understanding chaos will already help us so much, but then, it's also going to have connections with other things that we're now going to talk about. So what business does chaos have to do with gravity? And why are you interested in this?
Yeah, so I guess, so my background is more from the high energy point of view. And the first time I would say that chaos made an appearance in black holes was maybe some 10 years ago, where people understood that, well, of course, people understood much earlier that black holes had something to do with thermalization, that they could be viewed as some thermal objects with where you could associate some temperature to it, you could associate some entropy to it. So that was, of course, much earlier. But then, given this knowledge, it's not too far of a stretch to think that it will also have some chaotic properties, because chaos and thermalization are closely related to one another. But it was only really some 10 years ago that people actually tried to compute some specific probes of chaos for systems that are so-called dual to black holes. And with that specifically, I mean that people were interested in computing these out-of-time ordered correlators in states dual to black hole descriptions or geometries. And what they found there was that it was actually indeed growing exponentially with time with some exponent. And they later even understood that this exponent had to be bounded, and that black holes were saturating this bound.
Right.
So that was before even I started my PhD. That was some 10 years ago, or a bit more. And that's also only one of the facets of the chaos in black holes. So of course you could say a lot more about this. But more recently, What I've been studying myself in more detail is another type of occurrence of chaos in black holes, and for this we don't so much look at the chaotic features of these states dual to black holes, but we delve into the black hole horizon. We go near the singularity of the black hole, and there are some old results, and by old I mean like late 60s, early 70s, that describe the evolution of solutions of the Einstein's equation near space-like singularities as being chaotic. Like the claim was of BKL, of these three physicists, was that the generic motion near a space-like singularity is typically chaotic. And so that's currently mostly the type of chaos in relation to black holes that I'm interested in and studying.
Right. So is this how, so the fact that this near singularity, or the BKL, what BKL told us, that, this chaotic dynamics emerge in this limit, is that why, was that the connection to the arithmetic chaos thing?
Exactly, yeah.
I see.
So specifically what they show is that, so of course the Einstein's equations usually are very hard to solve in generic situations. But what they taught us is that near the singularity, some decoupling limit emerges, where you can view different points on the spatial slice that evolves towards the singularity. Different points decouple, and this dramatically simplifies the Einstein's equations.
Okay.
And this dynamic you can then solve for. And you can in fact reformulate this as this billiard dynamics. So this dynamics then describes the evolution of metric components. And so in particular, whenever this dynamics is chaotic, the type of pictures you could have is that the space-time sort of stretches and is getting compressed in different directions, and this motion is happening in chaotic ways. So one direction might be compressing at some time, but then will be stretching at some other time. And as we evolve towards singularity, you have this chaotic dynamics taking place at every point on your spatial slice. And so the coordinates on these billiards are really metric components. So they live in metric space.
I see. So like understanding properties of this dynamics, what exactly is going to tell us about gravity? So
one of the hopes is that first there's this observation that if you look at examples of gravity that you might care about, for example, 4D gravity, pure gravity, you don't add any matter, just look at Einstein-Hilbert action that describes gravity in 4D. And if you try to compute the billiard that corresponds to that specific setting, you find precisely the fundamental domain of SL2Z, or half of the fundamental domain of SL2Z. So you see this arithmetic chaos appearing. And then you could ask, okay, is this specific to this one choice that I made, like 4D, no matter added? But it turns out that even in the cases that you could arguably care most about, which is 10-dimensional string theory, if you look at the bosonic sector thereof, it was shown in some 20 years ago that in this much more complicated setting, somehow arithmetic chaos also appears. And this might make it look like this arithmetic feature may be fundamental. This is something we just don't know the answer to. But it is definitely interesting to ask the question. Of course, as you approach the singularity, at some point classical physics is supposed to break down. It's just not going to describe the physics all the way up to the singularity, because at some point the volume, for example, will be Planck-sized scale, and then you shouldn't be trusting the classical Einstein equations anymore. But then you want to know what will replace this. And one question is that we don't know the answer to, will this arithmetic aspect survive these corrections that you have to apply to be able to describe things.
I see.
And if suppose it does, then arithmetic chaos might be a guide to tell you exactly what type of things you're supposed to add. So that's sort of one of the hopes of why it's interesting to have a deeper look at it. Yeah.
I see. So it's an absolutely interesting problem. Walk us through how you got interested in this problem. Was it like we working in similar areas and you stumbled upon this, or was it like a well-defined problem that existed and then you started working on it?
I think so. I think it's a natural time to revisit this type of things. As I was saying, it's building on old stuff. As in,
I see.
It was developed in late 60s, early 70s, and of course throughout the years it had some revivals. Like I think the actual chaotic aspects were very actively studied in I think the 80s. So it's not like it completely stopped afterwards. Of course, it's a super interesting topic. It's one of the only places where you can actually write down or understand to a certain extent generic solutions to GR, because you're in this decoupling limit, things simplify, and you can do a lot of stuff which is very unique.
Right.
So definitely throughout the years, people were interested in it on and off, depending on who was picking it up. And every time I think people were interested in it, new developments took place. But I would say now, given in the last 10 years what we understood about black holes and about their chaotic properties, it is definitely interesting to try to revisit these things, because in some sense, the chaos that's happening, the chaos that has been computed in terms of this OTOC, for example, the interpretation that has been given is definitely related to the scrambling that is supposed to happen inside black holes. That definitely has always been the key thing to try and understand in this topic. But it's, in some sense, what you're computing is some OTOC in the boundary theory in this holographic framework. So it's unclear what you can say about how things scramble inside the black holes.
Right.
Whereas this BKL stuff, it really is about some chaos that is happening in metric space near the space-like singularity. So one of the interesting questions is what are the signatures of this chaos from outside the black hole, right? And if you're in ADS, for example, you have some black hole in anti-de Sitter space, so it has a boundary. Are there any signatures of this chaos on the boundary, in the asymptotic region? So those were the initial motivations of my group in Cambridge and myself. And so answering the question of how it came about, I think for one it's the right time to do this. Second, my background was in quantum chaos, and I actually surprisingly, I think younger people may not have heard about BKL before a few years. I think I had never heard about it before coming to. So I moved 3 years ago to Cambridge, and before being there, before that Sean told me about this, who's my supervisor there, I just hadn't heard about it. And when he told me about it, I started reading these papers, and then that's how our project came about, and then we got sucked into this topic, because it seemed like it was the right time as well to try and duck these old things up and try to. So the first paper we have together, for example, with George Santos as well, is to try and construct a setup in the ADS CFT correspondence. So in ADS, we try to come up with a setup where you would find this mixed master dynamics inside a black hole. If you look at the only analytically known solution that we have of black holes is, of course, like Schwarzschild black holes, and these don't have this chaos. These are like, you can write down the metric, you can just see the nearest singularity. It doesn't have any of this chaos. So the question we try to answer is what do you need to do to the theory? How do you need to change it, modify it, so that you find this chaos this chaos near the singularity. And so that was the topic of our paper, and that's how it started.
I see. So you mentioned that this has been built on, the stuff that was done before. So I'm sure that people have been looking at the quantum aspects, but you just also mentioned that the gravitational connection was also kind of understood.
Yes, definitely.
I see.
So I guess I think people who don't necessarily care about gravity would be interested in arithmetic chaos just because they have this peculiar feature, but then they would have this there would be this bad side of the story that hyperbolic space, who cares? It's not, you don't encounter it in real life, so why should I actually care that there's this exceptional type of models that do not follow the usual conjectures about chaos? So that would be the mathematical side. That may be the words that they would use. But then if you're interested in the gravity side, those people first were interested in just near singularity dynamics, were solving these equations, finding this type of chaos, and then people noticed, it's related to PSL2Z,
right.
and these have this specific type of anomalous spectral statistics. And so I would say I think that's a history of how
the origin. I see.
It came about. And yeah, at first our contribution was really to try to understand this in the setup of ADS-CFT, to try and be able to say something about the interior chaos from hopefully outside. So that was the aim of trying to find such a setup.
I see. No, it's absolutely fascinating how many different areas of research sort of come together to solve a problem that people in the community really care about and should care about. Great. So let's move on to the tail end of our podcast. And now on the Knowmads Podcast, we really like to highlight stories of researchers and so on. And particularly this one, because historically STEM has been a male-dominated field, and you're a woman in STEM, and well, now we have more role models like yourself. Walk us through your journey, how you got interested in physics, and what were some of the challenges that you had to face along the way, and definitely point out some highlights that you remember and will stay with you forever. Of this whole journey.
Okay, so I guess, I grew up as just a girl who liked to do mathematics in school. So okay. I think I liked pretty much all the subjects, to be fair, but my preference was definitely mathematics. And then I think with mathematics, the point is that whenever it feels easy, it just feels fun. And I think that's also one of the drawbacks, is that whenever it doesn't feel easy, then it feels very hard and you don't want to do it, which is a shame, because I deeply think that anyone is capable of doing that. It just needs maybe the little push at first to see how fun it is, and to be able to start to think abstractly. But so as a kid, I just loved doing it, and then when you grow up, I got in touch with just like astronomy. I was fascinated, of course, by the sky, spending nights out with just friends, watching at the stars and looking at the stars. And I guess I was also very fortunate that in Belgium there's sort of camps you can go to, which are called astronomy camps.
Okay.
And then you just go there during the holidays and maybe a week or so, and you have more older people who come and give you lectures about stuff that you may not see in school.
Right.
And so definitely I think I went there when I was 14 maybe, and this just confirmed my feeling that I wanted to do this, because I definitely thought the lectures were not boring. And of course, I guess it's not everyone's cup of tea to go during the holidays. have some 3-hour lecture about some topic in physics or in astronomy, but I was definitely liking it. So then, okay, it was pretty clear that this is what I wanted to do. So then I went on to study physics afterwards, and it was all fun. So then I continued, and I guess I always knew in the back of my mind that I wanted to do research. I guess when I was very little, like maybe 12 or something, I wanted to do like accounting or something, because I just knew I loved numbers, but I didn't know of any of the other stuff. But then afterwards, once you get to know it in school, it was pretty clear that I just wanted to do research, so that I would be able to just think on a daily basis and try to... I guess at that point, whenever you start, it's not clear what exists. So then you don't know exactly. But then I tried to see if I was more of the experimental kind, and I wasn't. So then I think definitely the theoretical aspect was talking more to me. So that was a natural thing to do. And then I just did everything in Belgium, where I'm coming from. So then I was able to just continue doing master's, bachelor's, and PhD in Brussels. So that's why I did. And then after my PhD,
all at the same university?
Yes, all at the same university. I would say this is not the general rule, but it's quite common in Belgium that you would remain in Belgium to do like up to PhD. That's quite common. It's not. It's definitely some people would go from, say, Antwerp to Brussels or some other places, just because we don't have departments in all the types of physics in all universities. So then if you have a specific thing you want to do that isn't present at your university, you would move to a different city, but it's very common to just remain within Belgium to do everything up to the PhD. And then afterwards, given that I had to move and went to the UK for a postdoc.
I see. So you mentioned about, you said that anyone can do it. They just need that little push. Did you ever need that little push? And if yes, then was it an event or anything that sort of tipped you into this direction?
Yeah, no, I didn't need it, but I definitely, I've heard stories of people who are very smart and who might have needed it. So I definitely also know people who don't like math and who I tutored, and at some point, okay, they didn't love math afterwards, but they could see the fun parts whenever they could understand it. And of course, like, I understand that some people don't like it, like some people don't like chocolate, and that's totally fine. But I do think that in our society, given how school is taught, I think many people who might actually end up liking it don't like it just because of how it's taught and just the way everything goes. And I think whenever it's hard, you won't like it, and that's normal.
Right.
Nobody likes the hard way, I guess. So.
So you did mention in bits and pieces, but tell us who you're working with, where are you working right now, and if the things that you like about what you do, and maybe even things that you don't like about where you work.
Yeah, so now I moved to Cambridge 3 years ago in the UK. I was hired by Sean Hartnell, who is faculty there. In the meantime, now I'm funded by some other fellowship. But of course, I'm still working with Sean and with some of his students and with other people who might be in Cambridge or abroad. Of course, I also have some collaborations that I carry with me from my days at Brussels. And what was the rest of the question?
That the things that you like about your work, your advisor.
Yeah, I think he sort of touched upon it at some point as well. What I like about quantum chaos is the fact that it's not just a topic in high energy physics. It's also something that's very relevant in condensed matter. Yeah. And I like the fact that I'm able to explore different areas. Of course, there's different communities and things happen differently in the different communities. So I wouldn't say, I don't think I would ever say that I'm a condensed matter because I didn't grow in that community. But there's definitely questions that are super interesting to me from these high energy point of views in the domain of condensed matter as well.
Mm-hmm.
And I think that's one of the nice things about a topic like quantum chaos,
that you can work in both directions.
Exactly, this interplay between different communities, and it also allows you to have a broader picture about physics in general, because if you only ever do the same type of things, then you'll be very good at one thing. But I think it also allows you to maybe come up with different ideas if you get in contact with different things. So I think that's one of the, like, this bridge between different communities is one of the nice things. Like nowadays, what we also have to get into in touch with is like this number theoretic aspect because of this arithmeticity. And while I always loved math, I haven't studied math. So, and that's still a different step. So it's nice to be able to get in touch with this field, even though obviously I don't have the tools of a mathematician to deal with this type of things. But it's nice to be able to get into contact with these papers and try and see what we can use for our own purposes.
So what was like some of the difference between like the work culture at Cambridge and Brussels? That was like very apparent for you.
I mean, I think in Brussels we are a very little group compared to Cambridge. I mean, Cambridge has within DAMT, it still has so many different groups, right? And the only ones that I really get into contact with are the GR group, the high energy group, and then the quantum info group. Those would be the ones that I get in contact with, but then there's all the other ones as well.
Right.
Whereas at VUB, where I'm from, we have only like we get into contact with the experimentalists because of teaching and so on. And maybe photonics, but that's about it.
Okay.
And it's a very restricted set of people. Like, for example, when I was studying, we had, say, 2 theory professors, like in hierarchy theory, and 2 is not a lot. So then definitely, like, the biggest difference is the amount of people you get into contact with, and the amount of people, of course, that visit, because a bigger group will have many more people visiting as well. So then I think that would be, I think, the biggest difference, just the size of the people, the amount of people you meet, and just the size of the group that you see on a daily basis.
Yeah, especially when the problem that you're dealing with also needs, like, so many different ideas to come together to be able to fit in.
And also, I think for, like, of course, I'm definitely happy about where I did my PhD. But it's also, whenever you meet a lot of people, this also broadens just the way you think about physics, because you encounter so many other topics as well.
Right.
Just for example, if you only have so many theory professors in the group, then just the people you have lunch with, for example, either do the same thing as what you do or do one other thing, like roughly speaking.
Right.
Whereas if you have a lot more theory professors in the group, then the people you have lunch with will just have a lot, just a broader spectrum of things they do. And so, you just get into contact with more different topics on a daily basis.
So, did you apply to other places for a postdoc position, or was it just Sean? And if yes, then why Sean?
No. I think whenever you're done with your PG and you have to apply, you don't, like, usually people don't really know you, right? I mean, you're only like a baby in the academic
timeline.
Yes. So. Okay, I don't think anyone really knew me when I was applying either. So then what you do is you apply to all places that you're comfortable with going to. So that's why I did. So I applied to many places, of course, during the fall. Like I don't know, like maybe order 50, like
okay, so
plus or minus 20, like a lot of places.
That is the standard, actually. Yeah,
that is the standard. Yes.
Yeah.
So I just did that, and so I ended up in the UK.
I see. And in Cambridge, you really wanted to work with Sean. Was that like already in the back of your head?
Well, so I mean, the way it worked in this case is that Sean was hiring, so he had money
Vacancies
for
and
his
money, yeah,
grant,
okay.
and so the opening, like the job opening, was about him looking for postdocs with his grant. So then it was a natural thing to, because he was basically the one paying me. So it's a natural thing to have more contact with him at first.
Mhm.
But there's definitely, I think, as is the case in most places, I think there's definitely you're usually free as a postdoc to also chat with other people and see what interests you and work on the other things as well.
Nice. So and I'm guessing you're continuing at Cambridge for a few more years now.
A few more years, yeah.
Nice. So first of all, before closing it out, I should really thank you for doing this on a very short notice. I really appreciate that. And on that note, thank you for being part of the Knowmads Podcast, Marie.
Thank you for the invitation.